What do you say we get this last part in the series over and done with? It's a recap. Now once we get through with the recap, and I'm going to go through it kind of slow because I'm not sure I even remember most of it myself. I'll probably forget some of it, but you can always go back, to the previous videos and maybe pick it up. And when we get done with this video, there will be one more video for sure. Possibly two, but one more video for sure. So let's go ahead and just go through the power supply first, and you'll see that I have color coded pink and a bunch of green and pink and green. Now here's why. The power comes in from the wall. It comes in. This clock is no longer here. So this is grounded. The one side of the wire here is grounded. Comes in, comes up, runs through one half of the heater in the rectifier tube. It runs through one half of the heater, comes down around and supplies the plate voltage for that tube. It also supplies AC voltage to the remaining heaters in the 4 tubes. Okay, B2, 3, 4, and 5, I guess it is. Yeah, B2, you see, B4, 2, 1, and 3. Yeah, the remaining 4 tubes. Okay, this is the 5th one. Here it is now. Here it is rectified. The voltage is rectified from AC to pulsating DC, and then we run into a 75 microfarad filter capacitor or smoothing capacitor. I really like that term so much better. Now this tube, if you'll recall, the 35W4, you're only supposed to have a 40 microfarad filter capacitor off the, the tube. Wow, how come we've got a 75 here? You'll remember that they're able to get by with this 75, and they do need a larger filter cap there because there's not much filtration and not much more smoothing going on with this little resistor here. This is what I refer to as a cheap choke. Years ago they ran this. You would see the field coil on the speaker between these two capacitors, but and they use that field coil to filter it because inductors oppose changing current. Remember that? You bet. Well, the way they're able to get away with this 75 microfarad capacitor right here is by running the AC voltage through this heater and supplying it to the plate. And then it gives it instead of going wham and going into that capacitor, it sort of feeds it a little bit slower and keeps the tube from burning up. Okay, otherwise it would just burn up. I mean, if this tube had to constantly feed that thing, just bang, constantly feed it, which it already does, but this has a certain limiting factor, It's almost like what they call, I think, a varistor. As it heats up, it allows the current to flow more and more and more to the plate. The tube conducts more and fills this up at a more even and steady rate instead of being slammed in there, causing arcs through the tube. We don't want that to happen. Once it fills up your capacitor, it'll fill up the second one, but it right off the top of the 75 microfarad capacitor, it shoots up and goes out 110 volts. That's the first voltage source off this rectifier. Now that 110 volts that's the only place it goes, right here. It comes up, comes through the primary of the audio output transformer, comes over and feeds 100 volts to the plate of the 50C5 output tube. Okay, it says 110 volts right there. That says 110 volts right there. You'll remember a while back I drew a line between the two, see, to show you that they're connected. That's not hard. That's not hard. Anybody can see that. Okay, the 110. That's the only place, by the way, the 110 is utilized throughout this schematic, throughout the radio. Now, once the 110 is fed out, the voltage also goes through this 1500 ohm 2-watt resistor, and that's the old cheap choke thing, and it cuts the voltage down to 90 volts. And the purpose of that resistor also is to bring down the amplification of the pulsating DC, which sort of kind of maybe does a little bit of dampening, and causes it to smooth out even a little bit more. And then of course the 30 microfarad capacitor, filter capacitor, also does it. And out of the 90 volt source, I've got it green. All the stuff, it feeds 90 volts to everything you see here in green. Everything. Okay, and we'll go over that earlier or later. And that's about all there is to learn about the power supply. I can't think of anything. Oh yeah, this capacitor. Remember this capacitor here? That was the first one we did on the very first video. That was C5. It's there to any spikes that come down the power line, within reason. It can only do so much. You get little spikes that come down there. I don't know what would cause them. Maybe some lightning 100 miles away. I don't know. They'll come down the line. It will try to eliminate them to ground rather than feed them into the tube, which of course, where does it go? Through that heater. This is all one heater. Now it looks like you've got two heaters, but actually what you've got is one heater that's been center tapped. Okay, that's all there is to it. This will send high voltage, high frequency spikes to ground, allowing the 60 cycles to continue on. That's it for the power supply. I can't think of anything else to tell you. Now let's go up and pick it up where the signal comes into the radio. Okay, here goes the hard part for me, because I've got to kind of remember all this stuff. Remember, I was learning a lot of it along with you. Okay, the signal, all of the radio signals coming through the air, they all sort of they just coagulate right here. They just all mash together right here. And we want to pick one of them out of there by using the tuner. And of course we have the trimmer cap right here, which makes things even more accurate for this. This is the coarse, and this would be the fine adjust. We go ahead and we adjust our tuner to pick out the signal we want. The radio carrier with the audio frequencies sitting on top of it. We want to pick out, I don't know, any given radio station. By the way, I want to point something out here. Daniel, Cool Blue Lights, he pointed out, he said, John, I think you got the audio frequencies wrong of the human ear. You said 2 hertz up to 20 kilohertz. I said, yeah, I did. He said it's actually 20 hertz up to 20 kilohertz. He's right. I was 18 hertz off on the low end. So keep that in mind. It's 20 hertz up to 20 kilohertz. Won't make any difference, but I just wanted to point that out. That's very, very astute of him to notice that, to catch that. I just looked at the lower number wrong, I guess. Okay, here we go. The signal is tuned in. We hit resonance, and the signal is sent on into the converter, or the mixer tube, or the frequency changer. I like that one. Just like I like smoothing caps, I like frequency changer, okay? And we have the control grid here with the control resistor, which keeps this thing from conducting, keeps it at 0 until the signal comes in. We have the local oscillator down here. When you power the radio up and all the voltages are sitting out here where they're supposed to, they're just sitting there like a bunch of racehorses, they're in the gate, they're ready to go, all the voltages are where they're supposed to be. The tubes are sitting there just humming, come on, give me a signal, give me a signal. Then, when the signal comes in, boom, they're off and running. It's just like the horses being let out of the gate on a racetrack. They're off and running, and that's exactly what happens to these tubes. Picture each one of these tubes as being inside that gate. And they need, when that bell rings and that gate flies open, that's really what's happening here. The signal is the bell, and it opens the gate of each one of these tubes. And away it goes. The radio starts to play. All right, this little resistor here is simply an impedance matching deal. This resistor here is the grid resistor, like I said, control grid resistor that maintains that at 0. When the tube begins to conduct, a field builds up right here, and it cuts across over to here, and the frequency goes up, mixes in the converter tube along with the signal coming from the radio station, the carrier with the audio. And what comes out? 455 kilocycles, which is the intermediate frequency of this radio. Now keep in mind the local oscillator will be oscillating at a higher frequency than what's coming in here. Whatever we tune in here The local oscillator will be 455 kilocycles higher than whatever that frequency is, okay? Whatever that carrier is coming in from the radio station. In this particular radio, that is. Now, I had a radio a while back that was had an intermediate frequency of 200, and I think it was 260. I think I had one that was 265. I even had one that was 270 one time. Well, all that means is the intermediate frequency is 260 or 265 or 270, and it means that the local oscillator is running at 260, 265, or 270 above the frequency that's coming in. In this particular radio, it's 455 kilocycles, okay? Whatever the intermediate frequency is on your schematic, it'll be written somewhere. That's how many cycles higher the local oscillator will be operating from what's actually being resonate, whatever's this, has been resonated here and fed into the mixer tube, okay, or the converter tube. At this point, once it leaves, it is now the intermediate frequency, okay, intermediate frequency, which still has audio on it. It has audio. It's being modulated by the audio coming from the radio station. The DJ doing the talking, the music being played, whatever. Now, one thing I did not cover last time, you see this green right here? Now, that green is also 90 volts on the, up through the primary of the intermediate frequency first transformer here. It goes to the plate, but it also goes up here. I should have covered this, and I never did. That is what's called the screen grid. The screen grid, what is the purpose of a screen grid? It helps accelerate the electrons through the tube. They go too slow. Sometimes they're very slow. And that 90 volts right there will shove them through a lot faster and make them hit the plate a lot harder. And it just makes things work better. I mean, you can't have a slow operating tube. Now, come on. Anyway, that's what the purpose. And there's one other reason for a screen grid. Those, especially in a converter tube where you have all these grids. Look at them all. They cut down on the capacitance. The screen grid cuts down on the capacitance between each of the grids. That would be called inter-electrode capacitance, okay? And the screen grid going in there makes it smaller and smaller and cuts down on the capacitance, which would ultimately affect the conduction of the tube and the frequencies, the fidelity of the frequency going through. All right. We have 90 volts coming up here. It goes through the primary of the first IF transformer, magnetically coupled across here, and it goes straight into the intermediate frequency amp. Why do we need an amplifier here that says intermediate frequency? Because it's very dinky when it hits the antenna, and this kind of brings it up a little bit, the converter, but it's still too small to really be used by the rest of the radio. So we have to run it through an IF amp and get it even higher. Boop! We want to get it up. And after we run that through there, it comes out again, the conduction comes up, the plate conducts from the electrons hitting it. And the secondary is fed into the control grid with remember, we're still into the IF now. We still have the audio, we still have the modulation. And it comes out of the plate into the second intermediate frequency transformer primary, gets coupled across again. Keep in mind, we also have a screen grid right there. See it? 90 volts coming up here feeding the screen grid. Why do we need that screen grid? Accelerate the electrons through the tube and help eliminate inter-electrode capacitance, okay? I think that's what it's called. I can't remember the exact term. Inter-electrode capacitance. I think that's what it is. Anyway, it's coupled across a second time and fed into another amplifier right here. Right there, the 12. See, it says amplifier. Why? Because it's still too small. It's got to be higher. We want it higher. It'll come in on the control grid, or it comes in on this diode right here. Now, this tube has always been very confusing to me. What I want you to do is I want you to picture this control grid, not here. I want you to picture this plate, not here. Okay? I'm going to block them out with the pencil. Now, all you're going to see is the cathode and that plate right there, that small plate on pin 5. That's all that's in that tube. So what do you have? You have a diode. It goes from the cathode to the plate. It's a diode. And what happens is the voltage coming off this secondary is going up and down, the audio, up and down, up and down, up and down, up and down. And it's going to control the conduction of that diode. Okay, because picture none of this other stuff here now. That's not there, just a diode, a cathode and a plate. And what happens is the tube is going to conduct and it will send a signal out. It comes across, it's very difficult to explain for me. I understand how it works, but sometimes it comes across, it eliminates half of the signal that's coming in. And I'm going to stop right here and go to my drawing that I showed you earlier. What that diode does, this is what the modulated carrier, the intermediate frequency carrier, the 455 kilocycles. This is what it looks like when it comes into that tube and hits that diode. That diode eliminates half of that. So all we have down here is this right here. We have the lower half of the carrier, and we have the audio riding on it, either top or bottom. It doesn't matter. It eliminates half of that, okay? That's what a diode does. Now, once it eliminates it, then, let me see here, it sends the signal, it conducts from cathode up through here, from cathode to diode plate, or diode anode, I think is what that would be called. It comes down around. Make sure I get this right. This is very important. It comes down, comes around, goes through the volume control, goes back up this way through this capacitor. That helps eliminate some of the DC coming off of there. Remember, this is AC. This is what we've got right now. I'll show you how we got that. We went from here to there by eliminating the carrier. And I'll show you how that was done. Right now we're still looking at this audio. It comes, let me see where it comes up the volume control through the capacitor and over to the control grid and enables this. Now what happens, you don't have this. See, all you have now is a triode. We have a cathode, a control grid, and a plate. So what's happening here is the diode, this thing conducts, rectifies the voltage, it comes on around, or the audio, the voltage with the audio on it, it comes down around, comes down over here through the control grid, comes up through the capacitor to control grid, through the volume control, over, up through the capacitor to the control grid, and what's happening is the diode is controlling the triode. I hope that makes sense. The diode is controlling the triode, because what's hitting the control grid right here is this right here. Come on, camera. It's this right here, your audio, because the carrier, the 455 kilocycle carrier has been removed. Well, where did it go? It was there a minute ago. Well, what happens is right here, when the audio and the carrier, when it couples across, the carrier comes out of the secondary of the second IF can, comes across, goes through this 400 picofarad capacitor and on over to ground. You'll remember I beat that to death for about 2 videos. You should know that right here is where that carrier goes to ground. Now the audio, not only does the audio come from here down around and wind up through the volume control up here to drive the control grid on the triode part of this tube. Not only does it do that, it also becomes what's called automatic volume control voltage. This is a busy part of the entire circuit right here, and it's pretty confusing unless somebody actually sits down and keeps going over and over and over it. I taxed Brendan's patience on this quite a bit, but I didn't care. He's the mentor. He said, man, I just know how many times I got to explain this. Well, how about one more? That's just the way it is, Not only does it come down around and go through the volume control and control the diode, it also becomes ABC voltage right here, goes through this resistor, comes across, and fills up this capacitor. The voltage fills up the capacitor, whatever audio is in there, audio frequencies are in there, go to ground, but it fills up this capacitor. And basically what you have there is a potential. You have a voltage potential. I was under the impression that this thing would fill up with voltage every time it was needed by this tube or over here to the control grid of this tube. I thought it would just discharge. Actually, that's not what's happening. You're dealing with a difference in voltage or a potential right here. This thing charges and discharges according to the level of voltage coming out of here from the audio, okay? And how quickly that capacitor charges or discharges to about 63% of its capacity is determined by the size of this resistor. Now, if some of you looked up RC time constants, you'd already know that. I can change how fast that capacitor charges up by changing the value of the cap, or I can change the value of the resistor. You know, it's sort of like a bucket of water being filled. You know, I can make the bucket bigger, or I can make I can squeeze the hose tighter with my hand. I can determine how fast this thing fills and doesn't fill. And that becomes a potential that's felt on the control grid here, and it's also felt over here on this control grid. And if you got high voltages coming in, high audio voltages, spikes on, that's picked up, I don't know, whatever, high volume, high voltage, this voltage will come out of here, it'll go through the resistor, come over here, fill the cap, and stop that voltage from being rammed through again at an even higher voltage. It'll smooth it down. These two right here keep it from doing this real fast, the voltage going up and down all the time. The RC time constant generated by these two items right here, these two little components, will give it a smoother up-down movement on the volume. Okay, smoother up-down movement. It's like just like an ocean, instead of crashing waves. Okay, that's what it amounts to. All right, I've been talking for 6-7 minutes now. It's time for me to take a little coffee break. I'll be back in a second. Okay, we're back. I know that was probably pretty confusing with the way I went through it there, but the only thing I think you really need to know is that the diode controls the control grid, comes out. This is a plate, and that's a cathode. And as the current goes through, the signal comes out, comes down around, comes down this way through the volume control, up through to the control grid on the triode. I just want you to understand when you see this stuff. If I had known this a long time ago, it would have made things a whole lot easier when it was time for me to, troubleshoot and look at radios. The diode controls the triode. That's really the only thing I want you to know about that. And that the ABC voltage comes down out of here. The carrier voltage that's with it, the audio and carrier voltage, the carrier 455 kilocycles goes over to ground. The ABC voltage and the audio and voltage continue on down this way, comes across, the audio goes out, and you create a potential difference in voltage on what's here on the control grid, what's here on the control grid up through this line, and that's how you get your ABC voltage in order to work. If I made that clear somewhat, then you're dollars and cents ahead of me if you're a newbie, when you're first starting out. It took me a long time to figure that out. Old Brendan kept pounding on me until finally I think I got it. So I kind of understand it. Trying to explain it might be is a whole different ball of wax, okay? All right, now that we have the triode working as a result of the diode working, the audio comes out. Now keep in mind that not all of the carrier frequency, the intermediate frequency, not all of the carrier, the 455 kilocycles, can make it out to ground through this cap. Over time, these components change values and things, and it's coming in at a pretty rapid pace. So it's not 100% efficient. That's what I'm trying to get at. So what they've done is they put another capacitor here, and they put another capacitor here to pick up any stray that may still, be in the circuit right here. This resistor, and this is the K1 little dark brown packet where everything is sealed. It's sealed in. Just follow it out. The control grid comes across. This is your control grid resistor. Pretty simple. It's hooked to the control grid. Over here we have a resistor. What does that do? Well, it comes up, it comes across. It's hooked to the plate. That's your plate resistor, okay? Which, you got your 90 volts coming up through your plate resistor over to your plate. Over here we have, the last ditch effort to get rid of any carrier that sneaked on through. These two capacitors do that. Then we have another resistor. What does that do? Well, let's follow it up and come across, and it's your control grid resistor. Okay, it's connected to the control grid on the output tube. Now, Brendan said, you know, keep in mind that this here right here couples across the audio. It allows the audio to go through very easily. It's a 5,000 picofarad. He wanted you to know that, okay? It hits the control grid of the output tube, and the output tube conducts. And again, you've got your cathode resistor. This is self-biasing, what they call self-biasing. Look that up. The tube conducts, and the signal comes out, goes through your primary on your audio output transformer, and it's coupled across to your secondary, and then on out to your voice coil. And this tube, its function is more of generating power, lots of current, lots of current. You need that current to drive that speaker. You need that current to be, you know, coupled across here to drive that voice coil, because it's a mechanical action, okay? We won't do it if it doesn't have enough current. It'll just kind of lazily sit there and make just rumbly sounds. You got to get that voice coil going back and forth like that. It does that all the time. And then, of course, we have a tone control cap here, which is across the primary. It keeps any spikes out, and any high voltage spikes, that is, lets it go on down through the here through the electrolytic capacitor to ground. And you know, it should be rated at a very high voltage. You know, one time I meant to mention this, I don't know if I did or not, but I fixed a radio one time. I put 6,000 volt caps in there. I said, what the heck? I love overkill. All right, that's all I can tell you about this. Now, I want to tell you something else. Am I a genius at this crap? No, I am not. But there are two people out there on the internet who are. One of them is Dennis Carter. Dennis Carter, that's his YouTube handle. And he talks about all these little circuits and everything. He goes into it a lot more in-depth than what I want. The purpose of my video here was not to go in-depth. I just wanted to kind of give you an idea of what's happening along the way. So when you stick your probe in here, you say, gee, it says I should have 0.4 volts. Well, yeah, it's going to fluctuate, okay? Just like over here, we have negative 0.3 volts. Keep in mind your grids are always negative, okay? Always negative on the grids. There's a negative 4. There's a negative 0.4 right there. Come on, camera, focus. Oh, this is important. Negative 0.4. Over here you've got negative 0.5. And over here you've got negative 0.5. The control grids and the tubes should always have negative voltage. Keep that in mind. Unless it's some really weird setup that I've never heard of, never seen, never read about, and Brendan has never told me about. Negative voltage on the control grids. Keep that in mind, people. If you're going through here troubleshooting your radio and you do not have negative voltage, you need to find out why. And keep in mind right here you've got 0.5 volts on this one here, and you've got negative 0.5 volts on this one here also. It's all being controlled by how much this capacitor down here is charged. Okay? If you charge a little, charge a lot. That's why the voltage will fluctuate. It'll fluctuate. It's constantly changing all the time. Charge up, charge down. Charge up, charge down. And it's also, this capacitor also functions, just one more thing, is the RF return path to ground. As your RF signal comes in, resonates the tank, it's got to go somewhere, you know. So it goes on down through the cap to ground. That's it. The second guy I want you to look up on the internet is Rick McWhorter, All American 5 Radio. Those guys do an excellent job of discussing this. You want to go in a little deeper into what I showed you, then those are the two guys to go to that I know of right now. I'm sure there are many others out there who do an excellent job, far better than what I could have done. And I want you to look them up if you decide you want to go a little deeper into this. Personally, I don't feel like going a whole lot deeper. I'm not an electronics whiz kid. I'm too old to become one now. I should have became one 35 years ago. I'd probably be a lot richer today. But that's just the way it is, you know. I mean, I am real happy with what I've learned so far. And, you know, some of this stuff I'm going to tell you I didn't know. And the refresher was very, very good to go through this schematic and show the rest of you. So if you got any complaints, well, I'm sorry. Go see Dennis Carter and All American 5 Radio. They'll take care of anything I may have missed or slacked on or didn't go into deep enough. Okay? Well, that's it, guys. Next video, we're going to take a signal tracer and we're going to go through this radio and I'm going to show you how to signal trace. Now, signal tracing I can do. Signal tracing's fun. And I'm going to take my little Heathkit signal tracer and we're going to go through it and we're going to just show you how to do it, how you can find a fault in a radio. You know, I knew a guy one time, he repaired these radios all the time and all he ever had was a multimeter. So these guys that think they need all this fancy damn equipment, you know, you really don't. A multimeter will get them going and get them playing. And especially on the AA5s, AA6s, he was able to tune them by ear, actually, and line them up by ear. You can do that. It happens all the time, actually. So that's it for now. End of part 10. I appreciate everybody being here. If I forgot something, I apologize. And that's the best I can do. Until next time, this is John. Today is the 13th of November, 2014, and I'm going to go in that door, and there is an office in there, and I'm going to claim a shipment. Here's the package. Now, what's in that package? I'm not going to tell anybody what's in that package. You're just going to have to guess it. It came into this giant warehouse, and it is being loaded on the old Toyota pickup truck. Thank you much. I appreciate it. And there it is, safely in the house. And I'll tell you, wifey's real happy about it being there too.